Okay, hi everyone. My name is Andrew Murray, and I'm going to be presenting my extended abstract on joint chance-constrained probabilistic temporal networks via column generation. So this was performed at the University of Strathclyde with my supervisors Michael Cashmore and Ashwin Arulselvan. Okay, so the title is a bit of a long one, so I'm going to introduce like a small motivating example just to kind of give the idea. Basically, your friends asked you to go pick them up from the bus station. Somehow the bus is running on schedule, so it's going to be there in 10 minutes. And you have to drive from your house to the station to pick him up. Now, you need to arrive before he gets there, and you know that the time it takes you to get there can be described with a normal distribution, and say it has a mean of 8 and a standard deviation of 1. Now, you get 4 minutes of free parking at the station, which is good. But if you take any longer than that, then you have to pay this cost. And so basically, the idea is, how do you figure out when to schedule these actions such that you arrive? So you want to arrive as close to the time that the bus comes, but you don't want to leave it too long to have to pay for that extra parking. But if you leave it too late, then you also risk arriving after your friend gets there, and then he'll be very angry. So there's a trade-off there between risk and cost. Okay, and so basically the formalism I just showed you is something called simple temporal networks. So the most kind of simplistic version you see on the left-hand side there, it's just a graph, and the time points, the vertices are just time points that you can schedule, and the edges are just constraints on the durations between those time points. So you can see there B1 minus B0, the time between those two time points must be greater than 0 or less than infinity. That's just to say that B1 must come after B0. So a schedule is just an assignment of a value to all of those time points that satisfies all the constraints. And now often in these kind of problems, there's uncertainty. And so there's this general extension called simple temporal networks with uncertainty that models the uncertainty inherent in these durations. So they just use like a set bounded uncertainty. So yeah, basically this time point E1, you can't choose when to schedule. It's going to come at some point between 6 and 10 after E1. Probabilistic simple temporal networks are just a kind of natural extension on that as well, where rather than using this kind of set bounded uncertainty, they use a probability density function. So one really good property of these is that it's something called strong controllability. So what that simply says is that there's a single schedule that will work for any of these outcomes. So you can see up here in the top right, this temporal network, you would say that is strongly controllable, right? So the schedule at the top, B0 equals 0, B1 equals 0, B2 equals 10, is a solution regardless of whether E1 minus B1 takes value between 6 and 10. So this is kind of rarely applicable in PSTNs, obviously, because you have these unbounded distributions. And so you have all these outcomes in the tails of the distribution that it's not really practical to consider all of them. So what they typically do is they just kind of truncate these distributions between some lower and upper bound. So you see there that you have this kind of normal distribution with a mean of 8 and a standard deviation of 1, and then you introduce this lower and upper bound and truncate that. So essentially you now have a strongly controllable simple temporal network with uncertainty, but you also have this measure of the risk, which is just the probability mass in the shaded area to the left of the dotted line and to the right of the dashed line. And you can see that these lines are given as a function of the value that you assign to the time points involved in the constraint. So the kind of idea is that as you change the value of B2 and B1, you kind of move these bounds, and so you want to kind of move them to straddle that mode there. The other option is, of course, this relaxing the constraints of paying a cost. So the effect that would have, if you imagine this U here to be like a soft variable, so as you increase that, then your lower bound, this dotted line, reduces, and so it'll kind of move this dotted line to the left, and so you have to pay that cost, but then this shaded area on the left is smaller, so you have less risk. So naturally, this is something that we would call a chance-constrained probabilistic simple temporal network. So essentially, you just have a chance constraint. So you can say, for example, that 95% of the time I want this schedule to work, and I'll accept a tolerance of 5% on risk. So give me the minimum cost schedule subject to that tolerance on risk. And the kind of typical methodology they use currently is just they make a number of assumptions to simplify it so they can use linear programming. So for example, they use Boole's inequality, so they just calculate the probability of all these random constraints independently and then sum them and use that in the chance constraint. And then they just approximate these distributions with piecewise linear functions. So this is good, it's fast and it gives you good solutions, but it can be conservative, so it's not guaranteed to give you the optimal solution minimizing cost. You also can't model things like correlation. So for example, imagine the bus's travel time and your travel time are both uncertain, and that travel time could be dependent on other uncertainty factors like the traffic at that particular time of the day or the weather, for example. So to kind of overcome that, we've modeled it as a joint chance constrained optimization problem, and then we solve it via column generation. So basically, kind of this is the most basic form, kind of getting rid of all the other maths in the background, but you see this general form at the top. So your X here, your decision variables are just the time points that you can choose to schedule, and then these like relaxation variables that allow you to relax these bounds. And then Z there is just your vector of random durations. So these are the chance constraint there is basically the constraints containing these random durations. And so you can just decompose that as the cumulative probability function of that random vector. Now we are assuming in this case that Z is a multivariate normal distribution, which has the nice property that it's log concave, which means that negative log of that cumulative function is convex. And so your optimization problem is essentially just this. So you have a linear objective, linear constraint, and then just a convex constraint there. So you can see these figures are just to highlight the convexity if that wasn't clear. So you've got your bivariate cumulative probability function there, and then if you do negative log of that, you have this convex surface there. So the way we solve this, we kind of take inspiration from this reference bottom here, and we form an inner approximation of that surface. So basically what that means is it's kind of similar to the outer approximation that Cashmore before explained, except we do an inner approximation, right? So what we do is we evaluate this function 5z at a load of vectors z, which are these little red crosses, and then we just take the convex combination of all of those points using these lambda variables. So if you generate enough points, what you have is a good approximation of that surface. The problem is if you have lots of dimensions, then the number of points that you need can be arbitrarily large. And so it's not typically practical to solve it with all of these points. You can imagine that the computation of that multivariate distribution can be quite expensive, so you don't want to do that too many times, essentially. So what we do is you start with a small subset and solve this restricted master problem. So you can see there we just use little k instead of big K. All that means is that we use a few of these approximation points. So we iteratively solve this, which is just an LP. And after each iteration, we then figure out the next approximation point to include, so the best new approximation point. And to figure out, how do you define what the best new approximation point is, you just use the concept of reduced cost, right? So the approximation point, which if you were to include it in the master problem, then the objective would reduce the most. And the reduced cost is just the dot product of these, the coefficients in the matrix on the left, and then also your dual variables there. So we call this problem at the bottom the column generation problem, which I'm sure a lot of you are familiar with here. So essentially all we do is we iteratively solve these problems. Top one gives you an upper bound, and then the difference between these, if you solve this to optimality, gives you a lower bound, so you can kind of terminate it when you have an acceptable solution. And this is just a pseudocode of what I've just described, and a kind of idea just trying to highlight pictorially how that would work. And you can see there you're kind of generating these additional points and making that inner approximation. So we have some very preliminary results, but essentially what you see is we have significant improvements in cost. I say always better than the LP. The reason I say that is that essentially if you solve this LP, you get this vector, right? And you can just use that as your initial point. So essentially you start with the solution from the LP and you only add the approximation points that improve, and so you're always going to get there. It's also got this anytime property in that you can run it for as long as you want, and you can just return the best solution so far. Now, next steps. First of all, we need to kind of get a lot more test cases. We also want to try and improve the runtime. So we find that obviously you can see there the runtime is really restrictive. The reason for that is that evaluating the gradients of these multivariate normal distributions is really computationally costly. So we're kind of looking in ways that you can solve that column generation problem using some meta heuristic, like a genetic algorithm that doesn't rely on gradient computation. So we can kind of go between those two methods so that we still get a lower bound on our solution in some iterations. And then we also want to look at problems with correlation. Okay, thank you very much.
Rather than chance-constrained optimization, does it make sense to instead try to minimize expected constraint violation?
I mean, it would not be the same kind of thing, would you not?
Right. Yeah. But it'd be something to compare against, maybe it's a benchmark.
Yeah. Yeah, that's interesting. Any other questions?
All right.